working. Right, okay. So as you'll have heard from Gwyneth, the motivation of our talk came from a paper the five of us wrote, which has just appeared, in which we are analyzing the internal dynamics in wandering domains. And then our thoughts turn to the boundary, and can we relate the internal dynamics to the boundary dynamics in wandering domains? That was the initial starting point. So one theorem, which I will outline the proof of later on, but it's a special case of more general results, is the following. Supposing you have a simply connected wandering domain of a transcendental entire function, the orbit of U is UN, and supposing you find a point Z0 in U with the property that the iterates Fn of Z0 go to the boundary of UN, so they move closer and closer to the boundary of the component in sufficiently quickly that this sum is convergent. Then for almost every point in the boundary of U, this is almost every with respect to harmonic measure, the points zeta on the boundary do the same as the iterates inside. So the iterates inside may be behaving in any way you like, as long as they go to the boundary sufficiently quickly that sum is convergent. Then the iterates on the boundary will follow the iterates inside, as kind of illustrated in the picture below. Fn zeta will tend to get closer and closer to Fn z0 as Fn z0 gets closer to the boundary. So, however, as I say, this is a very special case of a much more general result. We found we started off with wandering domains and then gradually realized that the arguments we were using hardly depended at all on wandering domains in some cases. So the most general setting, I guess, for our results is that we have holomorphic functions f, fn, little fn, capital Fn, typically around, which map one simply connected domain into another. So we have simply connected domains U and UN. None of them are equal to the whole complex plane. And typically capital Fn maps U into capital UN. And the reason for using capitals will become clear in a moment. Our general question is, can we relate the behavior on the boundary of U of these Fn of zetas to Fn of Z0 inside the domain? Now, there are a number of special cases which I've put here. Let's see if I can just move this a little bit. In the middle there, we've got wandering domains, which is the original motivation. Capital Fn is little f iterated n times, U being a fatu component. That's obviously a special case of what we've been talking about above. Slightly more generally than wandering domains is to look at forward compositions. Capital Fn there is the forward composition of the little f's. That's really, in trying to decide on notation for this, we decided that capital Fn would always be the function we'd look at, because potentially it was a composition of other functions which we wanted to be slight generalizations of little f. So that's the reason for the notation. In that case, little fn would map one simply connected domain, un minus 1, to another. Now, in the situation of wandering domains, obviously we talk about iterates and orbits of points, and it's very hard to give up that language. And certainly I would talk about orbits for forward compositions, because there you have a sort of non-autonomous dynamical system. But I might even end up talking about orbits under capital Fn, even though there are no orbits, it's just a sequence of functions, capital Fn. Another familiar context here is to look at self-maps of D, the unit disk, where little f is a self-map of the unit disk, and you look at the iterates of that. And a classical example to look at is inner functions, and I'll be stating some results about inner functions in a moment. Let's go to the next slide. Okay, so Gwyneth will have defined this, and I'll remind you of the definition of something called the Dangerois-Wolf set, which is a name we've given, somehow inspired by the Dangerois-Wolf theorem. Okay, so before I define that, here is a basic theorem about internal dynamics or internal behavior of sequences of functions, even if there's no dynamics involved. Capital Fn, sequence of holomorphic maps between simply connected domains, Z0 a point in U. So supposing you know that the distance of Fnz0 from the boundary of Un, the domain in which Fnz0 lies, tends to 0 as n tends to infinity, then the conclusion is that that if you consider any other point z in U, Fn of z minus Fn of z0 will tend to 0 as n tends to infinity. So this is a way of saying that if the sequence Fnz0 tends to the boundary, then all other sequences tend to the boundary, but they tend to the boundary in such a way that they get closer and closer to Fn of Z0 itself. Now, the inspiration for this result came from the paper by the 5 of us that appeared in this year, where we had a first version of this for wandering domains. And we were interested there, not so much in the orbits getting close together, but whether the orbits tended to the boundary or not. And we proved the result in that case. Gustavo, our student, has a version of this theorem in which you're iterating a meromorphic function between multiply connected domains, but you're interested in the behavior of the boundary as you go, to the outer boundary. So that's a similar sort of result. It turns out in Theorem A here that this result is extremely general, and the way you prove it is to use a lemma that's in our 5-author paper, which essentially shows that if points are close together hyperbolically, then they have comparable hyperbolic density, which is hardly surprising, I guess. Right, in order to define the Dangeau-Wolf set, so this is going to tell you something about the behavior of the functions capital Fn on the boundary of the set U. So far, Fn's only been defined inside U. It might extend continuously to the boundary. For example, if you were looking at iterates of transcendental entire function, it would clearly extend continuously to the boundary. But in general, we're not assuming that. But for our results to make sense, you take your inspiration from what would happen if you had inner functions. They have radial limits almost everywhere, whose image values are, in that case, on the boundary of the unit disk. So we introduced the concept of a sort of radial extension of a function of this type. So in the picture, there's a function little f, which maps a simply connected domain U to a simply connected domain V, not necessarily mapping the boundary to the boundary in our case. The main thing is that f of U is contained in V. And then you look at a Riemann mapping from the unit disk phi U to U, and consider also the mapping that you obtain by taking phi of U followed by f. Now, both of those mappings have radial limits almost everywhere on the boundary of the unit disk. And you can use those radial limits to define a radial extension of little f to the accessible points of the boundary of U. They're in 1, or the accesses, the equivalence classes, if you like, of curves going to accessible boundary points. They're in 1, correspondence with the points on the unit disk, on the boundary of the unit disk, where there are radial limits. And you look at those accessible points and you ask yourself the question, if I go towards the point zeta on the boundary, say, along a path that's come from a radius in D, then what will happen in the image under F composed with phi of U? And various things can happen, but if you get a consistent definition of what the radial limit is, as in the case of the blue curve, its image is to a point f of zeta inside V, or the green and the red curve, they tend to different accesses. The domain U on the left has a slit in it, but over in the image, over in V, their images go to the same point. So that's what I mean by consistent. If I look at that boundary point of U, where the red and the green curve approach, then I can give a well-defined definition of little f at that point. Now, of course, you'll probably be able to think of extremely unpleasant simply connected domains in which you're not sure whether there actually is a radial extension. In our theorems, we state results about what happens at the points where there is a radial extension. And in this talk, I'm going to assume that the radial extension can be defined almost everywhere with respect to harmonic measure. So I'm looking at domains with that property. In that context, then, the Donjoy-Wolf set of capital Fn is the set of zetas in the boundary of U such that Fn of zeta follows Fn of z for all z's in U. So in particular, we're interested in the case when the orbits, as I shouldn't call them, where the sequence Fnz inside tends to the boundary, and then I want the Donjoy-Wolf set to be the set of points where the behavior on the boundary is identical to the behavior inside in this limiting sense. So that's the Donjoy-Wolf set. I should say we had quite a discussion about what the Donjoy-Wolf set exactly should be, and this is what we settled on currently anyway. Okay, a motivation for the theorem I'm going to talk about is this dichotomy due to Aronson and Düring and Magnier papers some time ago. Very, very nice result, I think. So this theorem, which you can find in Düring and Magnier's paper, long paper on the dynamics of inner functions, ergodic properties of inner functions, in fact. Okay, so you have an inner function, f. This is a function from the unit disk to itself, analytic function from the unit disk to itself, which takes radial limits of modulus 1 almost everywhere. So in that sense, the boundary maps to the boundary. If the iterates tend, and I really can talk about iterates here, if the iterates tend to the boundary sufficiently quickly that this sum, a sort of Blaschke condition type, is convergent, then on the boundary, almost every point iterates towards the Donjoy-Wolf point. The function will have a Donjoy function, such a function will always have a Donjoy-Wolf point. That convergence condition indicates the Donjoy-Wolf point is on the boundary, and almost all boundary points in that case will converge to that Donjoy-Wolf point. I should say I put 0 in there, but it could be any point in D they would all behave in the same way by the previous theorem I mentioned, I guess. On the other hand, and this is why it's a dichotomy, as soon as that series is divergent, then the iterates on the boundary are, if you like, chaotic. Instead of converging to the Donjoy-Wolf point, they do somehow completely the opposite. The formal definition is recurrent, but if you think of it as one consequence of that, which is that the iterates are dense in the boundary of D for almost every zeta in the boundary of D. So there's a major dichotomy here going on. In case A, in terms of our Donjoy-Wolf set definition, the Donjoy-Wolf set has full measure because the iterates on the boundary almost everywhere are doing the same as they are inside. And in the second case, it's 0 measure because there will still be a Donjoy-Wolf point somewhere, but the iterates are not converging to it. So, obvious question, when you see this theorem, does this dichotomy hold in our general setting? And the good news is that the part A of the Donjoy-Wolf, part A of the dichotomy does work in our general setting. So I've stated this as Theorem B, which is the more general version of the wandering domains theorem that I stated at the beginning of the talk. And later on, I'll come back and say something about the proof of this, and I'll say it in the context of the wandering domains. So now we just have a sequence of functions, U mapping to UN. I'm assuming a full radial extension there, and that there exists a point Z0 in U such that this sum converges. And you'll see that it's all about the distance from Fn of Z0 to the boundary of UN. So that part of it's the same as in the dichotomy part A. But now I've got a power alpha. And in general, in this most general context, to get a positive theorem, you need alpha to be a half. In other words, you need the sequence to be converging faster than in the ADM dichotomy. But if the boundaries of UN are smooth, and let's not be too precise about that, but obviously a unit disk is smooth, has a smooth boundary, then you get alpha equals 1 in that case. The conclusion is that for almost every zeta in the boundary of U, with respect to harmonic measure again, then Fn of zeta has the same asymptotic behavior as Fn z naught, and indeed as Fn of z for any z interior. So that's a case where the Donjoy-Wolff set in this case has full harmonic measure on the boundary. Now, to show that alpha equals a half can't be improved in general, well, you'll see from the proof that the value of alpha depends quite significantly on the behavior of the boundary. And the worse the corners are, if you like, on the boundary, the smaller alpha has to be in order to get a theorem, and alpha equals a half is required in the most general situation. Our example to show that alpha equals a half can't be improved, where you have to have alpha equals a half to make this theorem work, is self-maps of a cardioid region. And I'll say a little bit more about that later. As I say, if you have regions with corners that you can sort of say the corner is no sharper than this, then you can arrange for alpha, values of alpha between a half and 1. But the extreme cases are in a way the most interesting, the smooth case where alpha equals 1, and the most extreme case, which must include, which you need for wandering domains, because their boundaries are hard to predict how regular or irregular the boundary of a wandering domain is. Okay, but what about the other here? What about the bad news? Can we generalize ADM part B, when the sum is divergent? So you might ask yourself, can I prove a theorem like this? Suppose I make it as simple as possible. I take self-maps of the unit disk, and I assume that sum is divergent. Could I get a result about the behavior of Fn on the boundary and that it is chaotic? That's an awful lot to hope, but what about, let's make it more special. Supposing you make your capital Fn to be the forward compositions of, let's make it as nice as possible, inner functions. After all, that's only a small generalization of the previous theorem. In the previous theorem, all the inner functions were the same, and the theorem held. Well, it doesn't take you very long to realize that you haven't much hope of getting a generalization, such a generalization, because there's a very simple example with Möbius transformations, which is always worth bearing in mind. So if you take any sequence an on the positive real axis, converging to 1, a naught equals 0, and it doesn't matter whether the sum is divergent for this example, but you can obviously assume that the sum is divergent. Then the capital Mn is a composition of little mn's, but the main thing is that the capital Mn of z is simply z plus an over 1 plus anz. So that Möbius transformation maps 0 to an, so the orbit, if you like, of 0 is verging towards 1. I don't have to specify what the little mn's are, because capital Mn, Möbius transformation is invertible, so I can always find little mn's that will build together to make my capital Mn. Well, certainly in this case, capital Mn of z converges to 1 throughout the interior of the disk. It does at 0, it does everywhere. But it's not very hard to show that it actually converges throughout the whole of the closure of D, apart from the point -1. -1 never goes anywhere, but all the points on the boundary, other points on the boundary, will converge round to 1. I can think of 2 quick ways of doing that. One is to use the fact that the cross ratio is invariant under Möbius transformations, and perhaps an even simpler way is to map the whole thing to a half plane, and where the mapping is very simple, and you can see that the boundary also does the same as interior. Okay, so Here's a warning counterexample. On the other hand, Möbius transformations are really very special. The Jean-Wolf theorem itself doesn't react well to having Möbius transformations in. Sometimes it works and sometimes it doesn't. So you might then say, well, what about Blaschke products of higher degree? So here's an example which shows that even with Blaschke products of degree 2, you're not going to get a result, at least not without some further hypotheses. So here we look at the little bn's. The bn of z is the square of the previous Möbius transformation I was looking at. Z plus mu n over 1 plus mu nz all squared, so that's degree 2. And I'm going to choose the mu n's extremely carefully, so they decrease to a third and do various other things. Why is a third of interest? Well, a third's of interest because if you replace the mu n by a third, then this Blaschke product of degree 2 would, of course, have a fixed point at 1, and it would be a parabolic fixed point. The derivative there would be 1. With the mu n's larger than a third, the derivative is less than 1. So 1 is an attracting fixed point if mu n is greater than a third. Then if we choose our mu n's carefully enough, what we can get is that the capital BNs, the composition of the little bn's, you'll see there's a theme going on here in terms of capitals and lowercase letters, that satisfies the divergence of Bn of 0. That Bn of 0 is tending to 1, but that sum is divergent. The fact that Bn0 tends to 1 means that Bn of z, for all z in the disk, will converge to 1 throughout the interior of the disk. But if you choose your mu n's carefully enough, you can make a disk around a whole disk around 1, well, an arc around 1 on the boundary also converge towards 1. So how does that work? Well, here's a quick sketch of the proof. Each Bn, as I say, does have an attracting fixed point at 1, but they get less and less attracting as you converge towards, as mu n converges towards a third. So for each of those, there'll be an arc, An, so the Bn maps that arc inside itself. And the intersection of the arcs is just the point 1. And what you want to choose your mu n such that Bn maps An not just inside itself, but inside the next arc, An plus 1, which is shorter. So it's quite a delicate choosing that you have to do. And if that's the case, then of course Bn will tend to 1 as n tends to infinity on the original arc, the arc A naught of B naught, if you like. And so the result will hold. So a comment to the margin, work in a half plane. I said the previous example works simply if you look at it in a half plane. This one, it's even easy. It is also the case that if you work in a half plane, the calculations are less fierce, but they're still, at least as far as we were concerned, there were quite a few calculations to do to make this example work. So an arc converges to 1, but what about the pre-images of an arc? This is what we always do in complex dynamics. We look at the pre-images. Well, you have to be a bit careful because when you look at a pre-image, you might be starting with the wrong B1. But you can still look at appropriate pre-images of these arcs and find pre-images that do converge to 1. So a good question is the union of those pre-image arcs dense in the disk? And maybe it has positive measure. These are things we have tried to show and have not yet managed to show. So there's some interesting questions going on there. Right, so this is all bad news so far, but there is some potential good news. And I only say potential good news because here's a different Blaschke product example. And this Blaschke product example was constructed before the previous one. So the first things we tried to do were to prove, to find conditions under which the second dichotomy, the second part of the dichotomy did hold. So here is a case where it does hold. It's rather special, but even so, it may point to what you might be able to, how you might be able to get a version of that second dichotomy. So what's going on here? Okay, so we choose our sequence AN again, increasing to 1. This time we definitely require the sum of 1 minus an to be divergent. So an is not going to 1 too quickly. We then define a little bn and a capital Bn. And I think if you look at the first bullet point first, it's a little clearer. The first bullet point says that capital Bn is the composition of the little bn's. And what it works out to be is that Möbius transformation preceded by z squared iterated n times. So the definition of the little bn above is just what makes that work. The key thing to think about is the capital Bn's being capital N of z to the 2 to the n. And this certainly tends to 1. It's easy to see for z in the disk. But we're also able to show that the Bn of zeta have the boundary behavior. This is dense. I won't use the word recurrent because we're not looking at iterates here. But Bn of zeta is dense in the boundary of D for almost every zeta in the boundary of D. And it's this example in the unit disk which we transfer to the cardioid by simply using the standard mapping. I mean, the cardioid we use is the one that's in the center of the Mandelbrot set, just because we happen to know the conformal mapping that takes the unit disk to that cardioid. Any cardioid would do, or you could probably do it with a disk with a slit in it, but that came to hand easily. And the key thing here is that you can choose your AN tending to 1 to make that cardioid example work. So you have freedom over what the ANs are tending to 1. You can make them tend to 1 at any speed you like, as long as that sum is divergent. So I've said that the BNs are a Möbius z squared iterated n times followed by a Möbius transformation, and the the z to the 2 to the n is the same for, well, it's the same formula, but the Möbius transformations change as you go along. Okay, so there's this, I put proof in inverted commas, there's a key fact in the proof, and the key fact has nothing to do with the Möbius transformations. It's all about, or not much to do with the Möbius transformations, it's all about a property of z squared. So I've called z squared g of z, I've defined epsilon n to be 1 minus an, so the sum of the epsilon n's is divergent. And I've defined capital AN, this is a subset of the unit circle, which has the property that if you iterate z squared n times, then you land in the disk, the center -1 and radius epsilon n. So you're changing two things here. As the value of n changes, you change the number of iterates. So you take more and more iterates as n increases, but you make the disk smaller, but it's not too, but the epsilon n's are divergent. And the fact that you need in order to make the example work is that if you look at the set of zetas in the boundary of the unit disk, which lie in infinitely many of those sets AN. So the sets AN will be unions of arcs. Every time you go back, you look at the further pre-image of one of these disks, you'll have twice as many arcs. But the set of zetas that lie in those arcs infinitely often, which is what you want in order to make the example work, has full measure, the boundary of D. Okay, so having thought that there might be an example like this, there was the stage of trying to prove that it has full measure. How on earth do you do that? Well, the sets AN themselves, if you work it out, all have length epsilon n, or 2 pi times epsilon n. So the sum of the lengths of these sets, which you're trying to look at the set of points that lie in infinitely many of them, is a divergent sum, which immediately suggests the Borel-Cantelli second lemma. The original proof, incidentally, in Dering and Magnier used the Poincaré recurrence theorem. That doesn't seem to be useful in our situation, but Borel-Cantelli, we thought potentially would be. So here is a version of Borel-Cantelli, much more recent, 2002, I think. You have a collection sets of the unit interval whose lengths, the sum of their lengths is divergent. in the original Borel-Cantelli, to get a conclusion, these sets would have to be disjoint from each other. Then you would get the conclusion that the set of points that lies in infinitely many of them has full measure. Petrov weakened that assumption, the assumption of independence, essentially, to show that as long as they don't intersect too much, the length of their intersection is bounded by the lengths of the sets themselves with an absolute constant c, then you get a result that says that the length of the points that lie in infinitely many of them is greater than or equal to 1 over c. And that enables us, by studying these sets AN in our Blaschke product example very carefully, to show that the set we're interested in doesn't have full measure, but does have positive measure. And then there's another trick we can use to show that we can go from positive measure to full measure. And that's to do with the fact that this family of sequence of functions is what's called contracting, so that we'll talk about in the next talk. I've forgotten when I'm supposed to finish, Letitia. Could you tell me whether I've gone over time or not?
You still have time. Let's see, you started at 20, you have 15 minutes.
Oh, excellent. Thank you very much. I was forgetting when I was supposed to finish. Thank you very much. Okay, so that's in a sense the bad news, or possibly good news, because I was rushing a bit there in the previous slide. Given that this family has this property of contracting, as I say, Vasa will talk about the consequences of contracting in the next talk. It makes sense to ask the following question, which is to go back to our question about can we generalize ADM part B, that dichotomy? Well, a natural thing to do is to add the hypothesis of contracting in here and ask, can you prove that result in the situation where you have the extra hypothesis of contracting, which in fact is present, but indirectly, in the original theorem of Düring and Magnier. Okay, so let me say some words about the proof. So this is the theorem I stated at the beginning about wandering domains. Remember, the hypothesis is that the iterates are going to the boundaries of the wandering domains sufficiently quickly that this sum is convergent. So I've listed below the 3 tools that we use in this proof with a brief description of each one. So Loebner's lemma to start with, very useful result, which was present in the Düring and Magnier paper, but I don't think they ever called it Loebner's lemma. They proved a version of it essentially from scratch for inner functions, specifically for inner functions. So the general Loebner lemma, I think this is the most general version, at least for holomorphic maps from the unit disk to itself. You have a set, a measurable set in the boundary of the disk, a point Z0 in the disk. Then starting on the right-hand side, these expressions are harmonic measures. So on the right, you have the harmonic measure in the unit disk of the set E on the boundary evaluated at f of Z0, the image point. And that is at least as large as the harmonic measure on the left in the disk at Z0, the initial point of the whole pre-image of E in the boundary of D. So that's Loebner's lemma, and I guess I should have said the pre-image of, no, that's okay. And what we can do is either apply it in the unit disk if we can find a situation where it works and where we can use it in the unit disk, or we can translate this lemma to our general context of holomorphic maps between simply connected domains U and V. And there will be a similar sort of statement. And again, we have to pay attention a certain amount to radial extensions in such a statement. So that's one tool that we use. Then there's the first Borel-Cantelli lemma, which people will remember having a much simpler proof than the second Borel-Cantelli lemma. So here you just have a sequence of sets in 0, 1, the sum of whose lengths is convergent. And you look again at the set of points that lie in infinitely many of these, and that always has measure 0. So in the proof, well, the proof of the first Borel-Cantelli lemma is straightforward, and we use the ideas of the proof, I guess, in our argument. And the third thing is the Milu-Schmidt inequality, which is an estimate for harmonic measure. The situation is drawn on the right. You have some simply connected domain U, a point zeta on the boundary, a disk. It's not a very good disk, I'm afraid, but a disk of radius r centered at zeta, which cuts off a domain V with zeta in its boundary. And gamma is the arc of the circle, or possibly arcs of the circle shown. And then you take a point for a point Z in V, you have an estimate for the harmonic measure at Z of gamma with respect to V in the domain V. And this estimate is in terms of the distance of Z from zeta, and the power a half comes in order to be able to deal with the most general kind of simply connected domain. And the constant there depends only on R, the radius. The extreme case is when the boundary is as thin as it can be. In other words, you might be looking at the tip, a domain with a slit in it, and you're making the estimate at the tip of the slit. And in that case, you would need the full power of the half. If your boundary, this is what I was talking about earlier, if your boundary is smooth, you can replace a half by 1, efficiently smooth, Benini smooth, or something like that. If it's Lipschitz and the corners are a certain size, then you can change the power to be somewhere between a half and 1. But in the general situation, in the most general situation, you have to have the power a half. Okay, so now a very quick outline of the proof of this result. So what have we got here? On the left, we have the domain U. We have the nth iterate mapping that to UN. So this is a Fatu component currently on the right-hand side. Fix R greater than 0 small. Put Zn for Zn is the nth iterate of Z0. And then we pick a point zeta n in the boundary of UN, whose distance, which is one of the nearest points to Zn on the boundary. So zeta n is not an orbit. It's just the nearest point, or a nearest point to Zn on the boundary. And then we draw a disk around the zeta n of radius r. And if n is large enough, then Zn will be inside this disk, and that's because we're assuming that our convergence condition tells us that Zn is tending to the boundary of UN. And then we let Vn, which contains Zn, and let gamma n be the boundary of Vn intersected with the closure of UN. So this is the kind of setup I had in the previous slide for the Milu-Schmidt inequality. Then take the pre-image of this small component Vn, the one inside the disk of radius r, take the component of the pre-image of that in U, and take the component that contains Z0, if there's more than one. And then we're going to apply Loevner's lemma in Wn. So this is a version adapted from the unit disk to Wn. That's the first thing we do, and then we'll apply Milu-Schmidt. So Loevner's lemma tells us on the left, we have a harmonic measure in the domain Wn, which will be simply connected, at the point Z0 of the pre-image of the whole of gamma n. So the pre-image of gamma n, I've drawn gamma n in blue, and its pre-image will be interior to U, and will look something like what I have drawn on the left. And that is less than the harmonic measure in Vn at the point Zn, Zn being the image of Z0 of the curve of gamma n. So that's a straightforward application. We can use that Milu-Schmidt inequality to say that that's less than a constant, depending on R, times the distance Zn minus zeta n to the power of half. So that now we've used two of the previous techniques. Now what you do is apply the maximum principle over in U, and you take on the right, you just have the pre-image of gamma n. So the harmonic measure on the right is the same as the harmonic measure above the left-hand inequality, the left-hand expression above. And on the left, you have the harmonic measure at Z0 with respect to the domain U of the pre-image under n iterates of f of all the points that haven't got near to zeta n by landing in Vn bar. So we think of Vn bar as points that are near to zeta n. If you take the pre-image of all the points that have not landed, if you take the pre-image, if you take the points on U bar that haven't landed in Vn, then that's the set on the left. And it's straightforward to see by the maximum principle. Well, if you think about where those points are, the pre-image of the points that haven't got into Vn, they can't be in Wn, so they've got to be cut off from Z0 by those blue curves on the left-hand side. The harmonic measure of the blue curves on the left-hand side, if you think of its value on those blue curves, is 1, and it's 0 on the rest of the boundary. You're comparing that to a harmonic measure which is 1 on parts of the boundary that are inside, if you like, the blue curves, away from Z0 and 0 elsewhere. So the maximum principle will tell you that inequality. And if you put together those two inequalities, then the one on the left is less than or equal to the harmonic measure at Z0 in U of the points that never get into Vn, is less than or equal to this constant, depending on R, of the distance from Zn to zeta n to the power of half. And that tells you that the set of zeta in delta U such that Fn of zeta minus zeta n greater than or equal to R infinitely often must have harmonic measure 0. And that's because the sum of the expressions on the right above, the C of R times mod Zn minus zeta n to the half, for fixed R, we know from our original hypothesis that that sum is convergent. And that tells you that this set of points has harmonic measure 0. Now that was a fixed R, but if you allow R to tend to 0 through a sequence, you deduce the set of points zeta in the boundary such that Fn zeta and zeta n have the same asymptotic behavior, that their difference tends to 0, must have full harmonic measure 0. So that's the proof for this case. In the most general case that we have, okay, so this was wandering domains, so the boundary mapped to the boundary. In the most general case, we allow the boundary to map inside UN, and the argument has to be a little more careful than that in looking at pre-images and where points lie, and the application of the maximum principle is a little more difficult, but essentially exactly the same argument works. And I think that's probably all I wanted to say. Thank you very much for your attention. And there's the picture again related to the Blaschke product example. Thank you very much.
Questions or comments? No, online audience? No. Okay, so let's thank Phil again. And Vas, stop